Today we're going to deal with magnetic lines of force. What are magnetic lines of force? Well, we say, well, if you sprinkle iron filings over a magnet, then you'll visualize, see, observe, I don't know what the word is, lines of force. But what are they? I mean, why do iron filings align along lines of force? Are they real? Are they physical? Are they imaginary? What are those lines of force? Well, so let's look at a picture here. Okay, this is the subject matter of today: magnetic lines of force. Okay, and I took the magnets out of there just so that it doesn't get in our way and it doesn't distract us. Okay, can you have a magnetic field? Can you have magnetic field lines without magnets? Okay, think about that question first. Okay, can you have a standalone magnetic field? No magnet, no nothing, no iron filings, nothing. Can you have a magnetic field just standing out there? Well, if you say that you can, then you should be able to draw it and say, well, what does it look like? Okay, and you can see that the so-called magnetic field is made of lines. Each line is individual. So we're talking about mereology here. We're talking about many lines forming a thing which you call magnetic field. Well, then the magnetic field is not an object. We got to look at each one of those lines if you say that those lines are standalone. What are those lines? I need to be able to have one of those lines alone for it to be an object, to be a valid object in physics. Okay? The field cannot be an object because, first of all, field is just a mathematical concept. It means a value at each point in space. That's not a physical object. And if you say the magnetic field is made out of these lines and that the magnetic field is real because it moves things around like iron filings and the lines move things around, well, we can't talk about the magnetic field. We have to talk about what constitutes the magnetic field, and for that we have to go to the line, and we're not going to talk about gazillions of lines. We're going to talk about one line. What is that line if it's real? And if you say, well, it's real, but it ain't, it's imaginary. No. It's black or white. It's either real or unreal. It can't be both. Okay, so please tell me if a single line is real. That's what we want to understand, okay? And this is the party line. Oh, by the way, there you see if you sprinkle iron filings, well, yeah, you can see certain patterns. And the pattern that you see on the bottom left is with two wires conducting current in the same direction. The wires attract each other, okay? And because they attract each other, it forms that pattern with iron filings sprinkled around them. And the question is, why do they? Why do they align in that way and not when the two wires are conducting electricity in opposite direction, which, by the way, creates a repulsion between the two wires? And why do iron filings sprinkled over them form that pattern, which you can see is totally different than the one on the left? Okay, so that's the million-dollar question for you today. You got to try to answer that question. Why? How? What is the mechanism that Mother Nature uses to do this? Because you can do this at home. If you have two live wires, okay, you point them in the same direction, you turn the electricity on, so now they're live, right? They're in the same direction, you sprinkle iron filings, you'll see that the iron filings will form that pattern, okay? Now you turn the electricity off for 2 seconds, you turn one of the wires around, okay? You turn the electricity on both of them again, and now you get that other pattern. How did Mother Nature do this magic trick? Because you can't see anything, and the only way you can see it is by sprinkling iron filings over the wires. But there's a real effect because iron filings are something you can touch and see. And Mother Nature is using something which is invisible, intangible, such as lines of force, magnetic field, whatever you want to call it, I don't care. And it's that thing is having an effect on something that's real, that you can touch, that you can see. So is she using spirits? Are you going to do this with black magic? Or are you going to say, no, there's something real in there that I can't see or touch, but is coming in physical contact with the skin of each iron filing? That should be your conclusion if you're a rational individual. If you're an irrational individual, you're going to do it with black magic, spirits, or who knows with what. Okay, anyways, here it is. This is the party line today. This is what the great minds of mathematical physics have come up with to explain what those field lines are. And if you read through a couple of them, you'll find the word imaginary in almost every one of them. A field line is a graphical visual aid That's what Wikipedia says. A vector field defines a direction and magnitude. That's it. So they're talking about math. What does Quora say? Well, one of the fellows out there says magnetic field lines inside the magnetic field are the what? Imaginary lines, blah, 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 blah. Another site, brilliant. Magnetic field lines are a visual tool. Another one, Hyperphysics, says the magnetic field lines can be thought of as a map representing the magnetic influence. Another one, Topper answers, magnetic field lines are imaginary lines. And the last one there, magnetic field lines are, or lines of force, are the imaginary lines, blah, blah, blah. They're just going to use it to visualize. So all these people, party line, right, is that all these lines are just imaginary. They're not real. We just put them in there to draw. That's it, just to make sure that, you can visualize something. But they're saying the lines themselves are not there. That's what they're saying. And yet they say that these lines move iron filings or compel iron filings to line up along the lines. So there's some spirit in there, some abstraction that is compelling things that you can see and touch to align in a certain way. Is there nothing there? Is that what we're going to conclude? Just because what? We can't see or touch it? You see where the problem is. Okay? It's just an issue of see and touch. We can't see it, so it's not there. It doesn't exist. Yeah, if that were the definition of object and of exist, yeah. Unfortunately for those who propose those theories, okay, those explanations, those are not the definition of the word object or the word exist. Object is that which has shape, doesn't mean you can see or touch it, and exist means that in addition, that object has location. Now we have those definitions, now we can make sense of these iron filings, of why they align like that. Okay, I like one fellow in Quora. He answered the following. There were several there, and this guy said something along the lines of everybody else, that they're imaginary, etc., etc. But I like something else that he answered, or that he stated, okay? And this is important, okay? And this is what his fellow says. He says, we do not know whether its theoretical entities correspond to ontologically real entities or are merely imaginative constructs that have pragmatic utility within a restricted domain. This applies generally to all physical entities posited by theories. I don't know what theories this fellow is talking about. I guess mathematics, is that what he's talking about? But I like that last sentence. It says, in other words, physical realism is philosophy, not physics. It's philosophy, he says, not physics. This is what they're saying. This fellow is supposedly a mathematical physicist. And involves an imaginative leap from empirical claims into non-empirical claims. This fellow says that because we cannot go to the lab and see or touch these things, then it's philosophy. He dismisses it as philosophy. He says that's not physics. Physics is what? Physics is math. Equations. That's physics. As far as this is what they're taught by rote in college. And this is what they repeat out there. So he says, don't worry about what's in there because we can't make sense out of that, but it's not important anyways, because if you can make sense of that, you're doing philosophy anyways. So, I always ask, you don't see gravity. You don't see, here, my famous experiment. You let go of the pen, and it falls to the floor. Always downwards, never falls upwards. I'll do it again, repeatable for it to be scientific, okay? So we got to do it at least twice, okay? And then we have to ask a China man on the other side of the planet to do the same thing, to do it there so he repeats my experiment to make sure that we covered all the bases. So we have a repeatable experiment. We let go of the pen, it falls to the ground. Is there something below the pen? Is there something above the pen? Can you see anything or touch anything other than air? The answer is no. So they say that in order to answer the question of why this falls to the floor, it's got nothing to do with physics. That's what this fellow is saying. It says that's got to do strictly or solely with philosophy. That's a philosophical question. So why a magnet attracts another is a philosophical question. What is electricity? Why does it turn on your light? That's a philosophical question. How does an atom work? Well, we don't know what an atom looks like, so we don't know how it really works. Those are philosophical questions, and so on. Everything they dismiss as philosophy. And so the first question that you should ask them is, why did they, from the start, try to answer those questions? I mean, if they just do math and put equations, fine. Stop there. Keep it in math. Don't call it physics. But what they do is they call it physics. And I'll tell you why. Because if they just do math and it has nothing to do, if they cannot explain the real world out there, then their math is totally worthless. It's garbage. They only have an equation which describes, but they can't tell me how the universe works. And so their math is worthless because it has no utility in physics. We have no way of answering any question in physics. So what they've done is, since they can't answer any question in physics, they dismiss that as philosophy. They say, oh, that's philosophy. So I ask you, I mean, do you think this is a question of physics? What causes or why the mechanism, right? This pen falls to the floor. Is that a question of physics? What do you think? Think it's just a question of philosophy? I thought philosophy was something else. Okay, so where do we go from here? Well, we have a present-day individual. His name is Matt O'Dowd. That's one of the ones that I researched out there, and this fellow says that he can explain the how, the why. Why he tried, I don't know, because if he's a mathematical physicist, he should stick to equations, to quantities, to measurement, to, that kind of stuff. Why does he cross the line into physics, genuine physics, and try to give you an explanation of how it works, how magnetism works in this case, okay? And this is him, okay? Little caricature of him, okay? We're not allowed to put their faces anymore in YouTube. That's why I have to use caricatures. Understanding magnetic fields is of fundamental importance to astrophysicists. Great. It's important. So is it philosophy or physics? He's saying it's important to physicists. Okay, so good. And he says, let's review how magnetism works. Is he talking about an equation? No, he's going to explain. He's going to try to explain to you how magnetism works. Did I understand correctly, or am I off the mark? Magnetic field lines, what do they do? Okay, so it seems like Mr. O'Dowd is going to try to explain magnetism, how it works. By how, I hope he's not going to describe that it picks up iron filings at such and such rate with such and such force or at such and such distance, and that he's going to do some measurement. That's not the how we're looking for. We're looking for the how mechanism. It's like, again, if you pull out a rope that's tied around a pulley, pulling a box upwards, you say, well, how did you pull the box up? Well, you don't want the person to answer saying, well, the box weighs 10 pounds and the rope has so much tensile strength and I had to pull it with so much force and invested so much energy. No, we don't want any of that. We want to know how you pulled the box up. And for that, it's very simple. You say, well, I tied a rope around a pulley and I pulled on the rope and that's how the box went up. That's an explanation of physics of how the box went up. We don't need to know force. We don't need to know energy. We don't need to know mass. We just want to know how you pulled the box to the second floor. Okay, your boss wants to ask you, how did you pull the box to the second floor? I say, well, I used a pulley and a rope. I pulled on the rope that was tied around the pulley, and that's how the box went up. That's an explanation of physics. These folks are saying that's philosophy. But now Mr. O'Dowd says he's going to try to explain it. And I'm not sure what he's going to explain, but I'm going to hold my breath. Okay, let's find out. And so he starts by saying the following. He says, imagine you can see gravitational fields. Oh my God. Yeah, if you can see gravitational fields, you're more powerful than God, because a field is a concept. And we don't usually see concepts. We can't see intelligence, we can't see love, and certainly we cannot see a field, and a field is a concept, mathematical concept. What is a field? Many values or many points in space, meaning many values around in space around a certain object. And that's not a physical object. That's a concept, and we cannot see concepts. But he says, it would mean seeing the literal threads of the fabric of space-time. Now he's getting more into my world. He's saying that there are threads, okay, some tangible thing out there, I guess, or at least something that has shape, right? He says, threads tug lightly towards the earth, tightly towards the sun. Lightly towards the earth, tightly towards the sun. Yeah, it looks like he's saying that the sun and the earth are somehow connected physically. And he says, think of electrons as being connected to all other points in the universe by invisible strands. Well, it looks like he's describing the rope model. Okay, so I guess he's on the right track. But the problem is that he says, you got to think of it. You got to make believe. You got to imagine it as if. So where in the quantum model do we find these strands, these threads? Do you see them anywhere? Do you see them in the standard model? I mean, they talk about it and they say, you have to make believe, as if. Why don't they make them real? Why don't they say, well, they are there? Because they're saying as if. Well, if it's as if, that means that way you can explain. But if you're going to use just particles, discrete particles that are not connected at all to each other, then yeah, you're going to have problems explaining. In fact, you're going to have to be doing a little bit of magic to be able to find out how one particle interacts with another one without anything in between. That's the issue. And so quantum, which is a discrete particle theory, cannot explain how a particle pushes or pulls on another one, unless push only through contact. But if they're separated, you can't either push or pull. So you cannot explain Mother Nature's universe with discrete particles, meaning that they are isolated from other particles by whatever. We'll call it space, vacuum, which they say is made of particles as well. So I don't know. They always fill in the holes with something, because otherwise they can't. And they cannot explain pull with that. They can only explain push. Okay. He continues, and he's going to try to explain, I guess, this. He says, magnetism is generated when electrically charged particles move. So he's going to say they move. Okay, so they move. And how does that generate, how does he generate magnetism just because a so-called charge with a concept, mathematical concept, 1.6 times 10 to the minus 19 coulombs. That's what charge means, just a value. And they're saying this value moves. You have this 10 to the minus 19 whatever moving. Right? When numbers begin to move, it's, you have too much to drink. Okay, so these numbers are moving. Let's concede. How does that generate a magnetic field? He just states that, insinuating that it's a particle. What's a particle? A zero-dimensional concept, meaning it's a value. That's all a particle is in quantum. So we have a charged number. This number moves, and somehow it creates a magnetic field or magnetism. So what are they talking about? What's the physical interpretation of this? What are we staring at? Charged particles tend to spiral around a magnetic field lines. And here's more or less what he's talking about. Okay, this is their notion. Okay, magnetic field lines form in concentric circles around moving charges. Okay, you can see how the charge is going around and around, and they follow, I guess, these arrows, which are supposed to represent the magnetic field lines. And the question is, how does that particle, which again is, you can see it's got all these locations. Okay, so that means that this particle is a discrete particle. It's moving around. Why is it moving around in circles? What's coming in contact with a particle for it to do that magic? That's what we want to understand. I mean, so far he's got magic. He's using a magic wand and saying the particle goes round and round and round. Yeah, tell me why. Don't tell me that it does. Tell me how it does so. Okay, maybe he does it at the next step, perhaps. Let me remove this for a second here. So maybe we just got to wait for him to finish his presentation. And so here's his finishing touch. Okay, this is where I guess he explains it. And he said, there's only one universal magnetic field. Some of the field lines connect to this greater magnetic field of the solar system and even to the galaxy. So I hope you understand and can explain to your son today or your daughter how magnetism works. That's it. That's all you'll find. So he hasn't explained anything. He hasn't explained why the charge goes around and around the magnetic field lines. He hasn't told us what the magnetic field lines are. We know that charged particle is just a number. So even if we can see that it's a little ball, a little particle, we still don't understand how that little ball goes around the field lines, why it goes in a spiral. We have no idea. It just is so. This is just someone measuring something out there that he doesn't see or touch. He comes up with this notion, and all he's got is a description. All he's done is a measurement, comes up with a description, and collects his Nobel Prize. He hasn't explained anything. Right? Okay, we can go back in time and find out that there was a gentleman. His name was Michael Faraday, good old Mickey. And he also said that he was probably the first one to propose that all these entities, things, atoms, okay, things are interconnected. He already had this notion that from doing experiments in the lab, he couldn't see or touch them, but he was intuitively convinced that they were all interconnected. Okay, somehow. He could not explain it, but he says, I'm convinced that these are all interconnected. So he came up with interconnection, but let's hear the whole story. This is where it stands. Okay, he says, maybe ask what lines of force are there in nature which are fitted to convey such an action and supply for the vibrating theory the place of the ether. Okay? I do not pretend to answer this question with any confidence. All I can say is that I do not perceive in any part of space, whether vacant or filled with matter, anything but forces and lines in which they are exerted. Okay? Forces obviously is an abstraction, but lines, hopefully he was thinking of something a little more solid. But here's where he starts getting very deep into this. He says, the view which I am so bold to put forth considers, therefore, radiation as a kind of species of vibration in the lines of force which are known to connect particles and also masses of matter together. He almost came up with a rope model. Given a few more years of life, he probably would have figured it out. Maybe, I don't know. But of course, he was influenced by a lot of mathematicians, and he was excessively respecting all the so-called eminences of those days, and so he kind of shirked from giving us a solid answer. And he says the ether lies between the particles and so carries on the vibrations, whilst it is by the lines of force between the centers of the particles that the vibration is continued. Okay, he said this really towards the end of his life, 1846. He was, I think he died in the 1860s. And so he was already imagining that there's something physical there. He already said it in 1852 there, I cannot conceive curved lines of force without the conditions of a physical existence in that intermediate space. So he was on the right track. He intuitively thought that all these masses, meaning atoms, were somehow connected because this one over here affected that one over there. He came up already in those days with the notion of entanglement. Okay, and here he will follow up on that. And he says the following. Okay, this is all from a letter, essentially a letter that he wrote to a friend. Okay, it says, for all the powers of matter, gravitation is the one in which the force extends to the greatest possible distance from the supposed nucleus. Okay, being infinite in relation to the size of the latter, and reducing the nucleus to a mere center of force. So we have this nucleus. Think of it as an atom. That's the best way you could imagine it. Remember, they were thinking of the Daltonian atom. It was just a little ball. That's all I imagine. And he's saying, that's the nucleus, and it's got all these ramifications that converge upon that so-called atom. Okay? The smallest atom of matter on the earth acts directly on the smallest atom of matter in the sun. How does it do that? And he's suggesting that there is some connection there, some physical connection. He's insinuating this, okay, intuitively. Atoms which, to our knowledge, are at least 19 times that distance, and indeed in cometary masses, far more, are in a similar way tied together by the lines of force extending from and belonging to each. Okay, so he's talking about lines of force. He doesn't know what they are, but he's saying they're connected by these so-called lines of force, which he said a minute ago, he says there's something physical in that space. Okay? What is there in the condition of the particles of the supposed ether? Okay? If there be even only one such particle between us and the sun, that can in subtility and extent compared to this. Okay? So he already had this notion that somehow these atoms from the sun to the earth to you were connected. But he couldn't make sense of it because, again, what? He couldn't see or touch whatever was there. He did a lot of experiments. He couldn't see or touch them. He said, well, there's nothing there, but I know there's something there. That's more or less where he stood on that. And here's his notion of entanglement. Okay, he really is the first guy to come up with it. Okay, he says, I incline to believe that when there are intervening particles of matter, being themselves only centers of force, they take part in carrying on the force through the line, but that when there are none, the line proceeds through space. Okay, so he's saying there's something going through that space. It's a line. That's the best way you could describe it. Okay, for suppose two bodies, A and B, distant from each other and under mutual action, and therefore connected by lines of force. If one of the bodies move in the least degree right or left, or if its power be shifted for a moment within the mass, then an effect equivalent to a lateral disturbance will take place in the resultant upon which we are fixing our attention. Okay, so he's saying this one over here affects that one over there. Entanglement. Right there you have it. Okay, so he already came up with that idea. Okay, for either it will increase in force whilst the neighboring results are diminishing, or it will fall in force as they are increasing. The occurrence of a change at one end of a line of force easily suggests a consequent change at the other. So he's treating all these lines of force that connect masses as real entities. Okay, and I think you can say that Mr. Faraday discovered entanglement or proposed entanglement, except that towards the end he chickened out. Okay? He chickened out. He had no huevos. Okay, and so he denied everything he said in that same paper, in that same letter. He says the following, okay, which is unfortunate, really. Give me a second here. Not sure why I can't see it. Okay, anyways, what he said at the end, I can't show it, I don't know why, it's not coming up. What he said at the end, he's saying, oh, by the way, I shouldn't have said all that because it was just speculation, and I should have really discussed it with other people and get their approval before saying all that. Okay, that's what he said at the end. Maybe I'll show it next time. But it's unfortunate that he backtracked, and at the end of that letter, at the end of, you could say, that paper, he said, you know, all this, it looks like they're all interconnected, but I take all that back because I should have really consulted with other people before saying all that. And that's how he ended his letter. That's really unfortunate. And maybe I'll show it next time. Okay, anyways, so where does this take us? Well, first of all, Maxwell said essentially the same thing. Okay, so he had the same idea. He says, field, the space in the neighborhood of the electric and magnetic bodies. That's how he defined field. In that space, there is what? Matter in motion. Okay. So he said that 13 years after Mr. Faraday wrote his letter, okay, and he said that shortly before he died also. He died relatively young. Okay, what do we propose? Well, we propose exactly what these two gentlemen suggested. We propose that all atoms are interconnected. We propose an interconnected universe, just like Mr. O'Dowd suggested, insinuated. He didn't suggest it. He says you have to make believe or imagine it as if, okay, but he never defined what those lines are, those interconnecting lines are. Neither did Mr. Faraday, neither did Mr. Maxwell. We're saying there are those lines in there. The only thing we had to do all these years is redefine the word object. It's not that which you can see or touch, it's that which has shape. You can't see or touch every object that has shape, every shape out there. Okay, and so this is what we're proposing. We're saying that whether on the one hand we have mathematical physics, they propose discrete particles which are not connected in any way, and we wonder how those particles interact, either pushing or pulling, if they are not in contact with each other. The only way we can make sense of it is under the rope model, and that is interconnectivity. Okay, so those are the two options. I don't think there's a third option, and what we're proposing is interconnectivity. Okay, so we think it's a powerful idea. We're doing the same thing as Faraday suggested, as Maxwell suggested, as Mr. O'Dowd suggests even to today, that everything is interconnected. We're not going to say as if. We're not going to say that you have to imagine it as if. We're saying they are, in fact, interconnected. And an object is not that which you can see or touch, it's that which has shape. And yeah, these interconnections have shape, but you cannot see or touch them. That's the only assumptions we had to make all these years. Okay, so here's how we see these lines of force. We're saying that all these lines of force are actual threads, and those threads come out of the atoms, the electron shells that encapsulate the proton stars. I've shown that in the past. I'm not going to go into a little detail here, but we're saying that these threads are coming from the ropes and from the electron shells that are bound to other electron shells, forming these long, what we call serpentines. When they move around at great speeds, they move these threads around as well, and the accumulation of all these threads is what forms that so-called magnetic field. Okay, that's what we measure out there, and we measure it what? Because we can see the iron filings that are affected by these threads. These threads move through the iron filings. Okay, they move them, and what they do is by doing so, they also magnetize the iron filings. So these are moving right through them. Okay. Okay, so let's move on here. And here we see the mechanism of attraction and repulsion. We can now superimpose these motions on top of the patterns we saw earlier with iron filings thrown over two wires first that conduct current in the same direction, and on the one on the right you'll see them in opposite directions. And what I'm trying to show here is that you can see that the patterns that are formed are that between the two wires you'll see that these iron filings line up as circles. Then slightly out, little distance outwards, you'll see that they form this figure 8. And finally, the iron filings, it's like if they circle both wires. And what is happening is that, again, the threads are moving around. When the threads move between the two wires, they move as circles. At some point farther out, you'll find out that the thread, as if the thread comes in and it gets pulled by the other thread in the figure 8 direction. Right at the bottom, you see that. And then the threads that are farther out, they just circle both wires. That's what we're saying is happening. And that's why the iron filings align along the so-called lines of force, which are actually the sweeping of threads. Okay? That's what the lines of force are. And in the case of repulsion, here you have one of the one of the wires, it's swinging the threads clockwise, and the other one is swinging them counterclockwise. So they meet between the two wires, and they push each other away. They kind of squash there in between. And that's exactly the pattern that you see when you sprinkle iron filings over them. So we can justify why the iron filings align along those patterns, because it's the threads that are moving through them. Okay? And those threads have an effect on the iron filings, on the atoms that form the iron filings. That's essentially what we're saying here. Okay? And we see this when we look at the mechanism of attraction and repulsion. I like to show it always with my two fellows, Axel and Rod. Okay? Here we have Axel and Rod, and we can see what's happening. They both swing counterclockwise, their ropes, and when you bring the magnets together, what they're doing is attracting each other. Okay? And remember, the one on the bottom is moving opposite to the ones on the top. So the tops are moving counterclockwise, the ones on the bottom move clockwise. Now, if you turn it around, now we're going to have repulsion, south against south. And what you see is, again, the threads are going to be clashing against each other, both on the top and on the bottom. Okay? So that's the mechanism of attraction. We can explain not only why the iron filings align along those patterns, but also why two magnets attract and repel because of the swinging of threads. Okay? And here one more time is the repulsion. Okay? South against south, the threads are going in opposite direction. The closer you get them to each other, the more resistance there's going to be, because why? You have more threads, the atoms are closer to each other from one magnet and the other. And so there are more threads intervening, so it's harder to push two magnets like south against south together. You got you've got a whole bunch of gazillions of threads pushing against each other as they swing around. Okay, so that gives you an idea what the threads are, what the lines of force are. They're the threads that are swinging around. Okay, and you might say, well, is that the case? Well, here's a little evidence. Again, this has nothing to do with convincing. It's just, again, an assumption. And you can take that as an assumption because you should be able to explain to your little kid how magnets attract and repel, whether you agree with it or not, but at least you can explain the mechanism with these threads. Okay, and here you see something that a lot of people don't know about, and that is that if you put a magnet underwater, the iron filings are picked up like one at a time. Okay, so that means that something is moving in that region we call lines of force. And those lines of force are, what we're saying is, swinging threads. That's why they pick up one of these at a time. Otherwise, you wouldn't be lifting one at a time like you see there. Something is in motion in that region. That's why they're being pulled one at a time. Okay, and I'm saying that at least the threads give us an idea of how magnetism could be working and how it attracts iron filings, in this case underwater, one at a time. Okay, let's go to the conclusions. Okay, on magnetic lines of force, what can we conclude from this? Well, here we have it. Okay, we have from Mike Faraday to Matty O'Dowd. No one has ever explained the physical mechanism of how magnet attracts and repels. So you have all these people on YouTube especially, and they say, oh, let me explain to you how magnets work. Not one of them explains how magnets work. In other words, what the mechanism of attraction is. What they're going to do is describe. And there's one, I think, either Berkeley or Stanford University, and what the fellow says is that the electrons of this magnet spin, and the electrons of this magnet spins, and because they spin, one magnet attracts another. See, they never explain. It's like you're saying, well, this top spins over here, this top spins over there, and because they spin, one attracts the other. Well, you still haven't explained how one spinning thing attracts another spinning thing if they're both discrete entities. So again, they haven't explained it. You need to explain the mechanism. And that's when they say, well, that's philosophy. So why did you try to explain it in the first place? Why do you say that you know when you don't know squat? Okay, that's the problem. And quantum mechanics has no physical interpretation because no mathematician has identified the invisible, intangible mediators. What? The lines of force. They say those are abstractions. Those are imaginary. You're not supposed to take them as real entities. And then what makes up a field? Well, all these lines of force. Mereology. What is a field? Many lines of force. Okay, so we don't care about the field. What is the line of force? Is it real or not? Can it move an iron filing? Can it interact with an iron filing or not? And the iron filing is that thing that you can see or touch. So you have something invisible which you cannot see or touch that's affecting something that's visible that's you can see or touch. Is that invisible, intangible thing a non-entity? Doesn't it exist? Doesn't it have form? How does it affect something that you can see or, and touch? It's like saying, you know, the ghost moved the curtain. Okay, what does a ghost look like? Oh no, it's not a real entity. Well, how did it affect the curtain, which is a real entity, which I can touch and see? And you're saying there's something out there that touches and sees or touches the curtain, moves it, but then you tell me there's nothing there, that thing, that ghost, that spirit is a non-entity simply because you can't see or touch it. And you can't draw it. You can't draw it because why? Well, because you've never seen a ghost. But that's what you're explaining, how the curtain moved. That's the same thing here. Okay, mathematicians dismiss elucidating the invisible intangible mediators as philosophy. So why do they continuously attempt to do philosophy, trying to explain, right, mechanisms, if it has nothing to do with mathematical physics, which is what? Descriptions. An equation is only a description. Okay, to visualize and understand the mechanism of magnetism proposed by the rope hypothesis, we need only to make the mediators visible. Draw it. Show me a picture. Show me the movie.